Hello and welcome, everybody. Today, we're very glad to have our own Balarka giving a talk on Gromov-Tischler theorems for symplectic stratified spaces. Okay, without further delay.
Okay. So I'll start with some preliminaries on symplectic manifolds. So what is a symplectic manifold? Briefly, it is a two-dimensional smooth manifold with a form and the form is said to be symplectic if two conditions hold. One is omega is non-degenerate, which means either you can think about the bilinear form being non-degenerate, or you can say that the omega wedge power n, which is a two-dimensional form, is non-zero everywhere, and d omega equal to 0. So omega is closed. Examples include some basic examples are m equal to r2n with omega 0, omega standard being the standard symplectic form, which if you put coordinates x1 to xn, y1 to yn, it would look like. So this can be generalized to cotangent bundle of any n-dimensional smooth manifold. These appear as phase spaces in classical mechanics, where omega is the Liouville form, which in generalized position momentum coordinates. So if q1 to qn are the position coordinates, p1 to p1 are the momentum coordinates, it will look like dpy wedge dpi. Another example is CPN, where the symplectic form is the scalar. More on this later. So in particular, that implies any non-singular projective algebraic variety would be a symplectic manifold. The Kähler form restricts. Okay. So before moving on to the next part, maybe I should say Darboux theorem. So this says that any symplectic manifold, m comma omega is symplectic, is locally like, so what does this word mean, right? I'll explain. R2n comma omega standard. So anything locally looks like this, the standard symplectic form of the Euclidean space. And what I mean by like is just it's locally symplectomorphic, in the sense that given any point P here, you can find a chart around it, which is diffeomorphic to R2n in a way that the symplectic form pulls back to symplectic form here. So these are local rigidity results. So if you want to think in terms of, if you want to say that this omega is like an analog of a Riemann metric, but it's antisymmetric, that this doesn't quite play out well, right? Because in Riemannian geometry, you don't get locally that every Riemann manifold looks flat. But that happens to be the case here. There is no local geometry. So let me move on to symplectic reduction. Okay. What is the basic idea? The basic question that I'm trying to address here is how to construct examples of symplectic manifolds. There are two ways of doing it. Like, how do you construct examples of manifolds, new manifold from old ones? You can either connect sum or you can quotient. You have such operations in the symplectic world also. I won't talk about connect sum, but I will talk about quotient. This is exactly what reduction is. Okay. So suppose this is a symplectic manifold. And G is let's just say compact to be safe. I'm not sure how much you need this assumption, but compact Lie group which acts on proper action should in general be fine. So definition. This action is symplectic if let's just say rho is the representation in diff-m, right, corresponding to this action. If rho star rho g upper star omega is equal to omega. So multiplication by g preserves the symplectic form. Okay. So this is actually equivalent to this. So maybe I'll write it like this. So this is equivalent to if you take the derivative of rho, that will give you a map from the Lie algebra of G to the Lie algebra of diff-m, which is just all vector fields on M. And then you take a vector V in the Lie algebra and push it forward by the derivative of rho. Okay. The Lie derivative of omega with respect to this vector field is 0 for all V in the Lie algebra. Well, this is sort of clear, right? You can just take G equal to exponential map TV. Sorry, yes. Yeah, thanks. Okay. This is further equivalent to I rho star V omega is closed. This follows from Cartan's magic formula, right? Lx omega equal to ID di omega plus ID omega, but d omega is 0, so you remain. Okay. So if M had the first Betti number of M was 0, then this would imply that this is actually exact. So you can extract a potential out of this. Okay. So let me give a definition with that in mind. This potential is important because this is like a conserved quantity. It's Noether's theorem, basically. So you say that action is Hamiltonian, or G acts on M by Hamiltonians, if there exists Lie algebra homomorphism. So let me just put Lie algebra in quotes for now. Homomorphism from G to C infinity M, such that I'll explain what this means. Such that the following diagram commutes. Yeah. So G to, if I take derivative of rho, that will give me a map from G to all vector fields on M. And there is also a map from C infinity M to all vector fields on M. How is this defined? You take a function, let's say capital H here, and you take and it spits out a vector field xh, which is defined as follows. You this is uniquely given by the following property: Ixh of omega is equal to dh. Okay, so if you think of omega and IV as a Riemannian metric, this is saying that h is the xh is the gradient of h, but this is a symplectic version of the gradient. Okay, this is called the Hamiltonian vector field. Corresponding to h. And I'm saying that there should be a map for this action to be Hamiltonian. There should be a map like this, which makes the diagram commute, and the map should be a Lie algebra homomorphism. Well, I know that this is a Lie algebra. What is the Lie algebra structure on this? It's the Poisson bracket. So the Poisson bracket is defined by, if you have two smooth functions, you just take omega of the corresponding Hamiltonian vector field. I never remember the sign here. Maybe I'm switching the signs. Okay. So what this means essentially is that you can extract out, it's not only true that these are closed, but it's also exact, and you can extract out the potential is not uniquely defined, it's defined up to scalars, but you can pick these sufficiently nicely so that the map here is a Lie algebra form. So these are not rare. In fact, if M has Betti number 0, then you can always do this. And if G is semi-simple, you can also always do this. Some cocycle vanishes. Okay. So any symplectic action is in those cases Hamiltonian. Okay, so any Hamiltonian action has a corresponding moment map. Okay. Okay, what is the moment map? Let me just say it sort of verbally. So you have a map from G to C infinity M. That will give you a map from G cross M to R, which will give you a map from M to G star. You just do something else. Yeah, you have a map G to C infinity M. That will give you a map G cross M to R, and that gives you a map M to G star. Okay, just do currying and currying. Okay, and what this means is sort of that this map can be explicitly written as a little m point here goes to the functional on G, which sends a vector V to the value of the potential of I rho star V omega at M. So it's exactly this conserved quantity evaluated at M. That's why it's called the momentum map. Okay. Yes. Xh is a Hamiltonian vector field, which is defined as follows. You take any function h, the Hamiltonian vector field corresponding to it is given by the unique vector field for which omega xh dash is equal to dh. Okay, it's like the gradient but symplectic. So fact, sorry, yes. So fact is that this is G equivariant. Whenever the action is Hamiltonian, I mean the corresponding moment map will always be G equivariant, and therefore you can define this. You define this quotient M, the symplectic reduction of M by the action of the Hamiltonian action of G on M, to be mu inverse 0 mod G. Okay. So what is this saying? It's saying that you take, so you can't just naively quotient M by G, that will have weird dimension of M minus dimension of G. Whatever quotient you're doing, you should get a symplectic manifold, so it should be even dimension. So basically this is quotienting twice. You look at the momentum map mu and then look at a gauge slice mu equal to 0. That's quotienting once in some sense. Okay, dimension reduces by dimension of G, and then you quotient that again. That is well defined because mu is G equivariant. Okay. So a simple example, I won't work out the details, but this is not so hard to check. You take M equal to R2 and G equal to S1, and G acts on M by theta x y, basically R theta xi y, right? Each x1 y1 plane, it just rotates by theta, and then you can check that the moment map is given by half norm x squared plus norm y squared. And in this case, 0 is not a regular value. Okay, so that's a problem. But thankfully, the group here is S1. So the action of G on this side is the coadjoint action. That's trivial. Okay, so it doesn't matter if you take 0 or 1. The pre-image, there will always be a G action on the pre-image. Okay, so therefore you can take this mu inverse 1 mod G, which will be exactly, let's say okay, CPN. And this is the description of the Kähler form of CPN. This is how I think of the Kähler form. You look at R2n, look at the unit sphere, look at the restriction of the standard form there, quotient by S1, and then descends to a symplectic form of CPN. Okay, so but the point is that this 0 being a regular point seems some essential thing, right? Because otherwise you won't get a manifold. So this is a manifold, in fact, a symplectic one. If 0 is a regular value, or if G is a torus, and then you have freedom to take whatever regular value you want here. What happens otherwise? You don't get a manifold, you get a singular space. So what are singular spaces anyway? So here, sorry, this still does. I mean, yeah, all the so this will be a stratified space. All the strata will have even dimension. Yeah. Yes. Yeah, I think that's true. Is there, yeah. Yeah, it has event dimension straight. I know. I don't know if it has an open dense straight. I mean, general. Maybe if maybe I'm not sure. I'm not sure. I have to think about it. Okay. So a stratified space is defined as follows. So this is a formal framework to work for working with singular spaces. Suppose this is a manifold. Okay, nothing symplectic here. We're just changing gears completely. And X is a subset. Okay. Suppose also that you have a collection of disjoint locally closed subsets of X, which partitions locally closed just means intersection of an open set and closed. Think quasi-projective varieties. Okay, and I is a poset. Okay, I'm indexing everything by a poset. I'll explain what this relation is. So yes, yes. And this action can be extended to all of CP. I mean, you want, oh, just the union of the neighborhood. Okay, man. Yeah. But would it not be a blow up or something? Yeah, seems like a blow up of that, right?
One of those
Okay.
then since we're going to do the ordination on manifold, which is regular manifold,
Yes.
then you look at the S1 action on that.
Yeah, which gives a projective bundle.
Give you the comfort.
Okay.
This is my guess.
Okay.
My guess.
Okay. 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 I'll think about that example. Sorry, which one? Ah, right. Yes. I should get -1, right? Yeah. Thanks. Okay. All right. So suppose that you have a subset of your manifold M and it decomposes as a, so there is a partition. I have a partition by locally closed subsets of X. Okay. So also assume that S alpha are all smooth submanifold. So not necessarily properly embedded, these are non-compact, but they are smooth submanifolds and they satisfy the following property. S alpha intersects, so for all, okay, actually I say S alpha intersects S beta bar if and only if S alpha is contained in the closure of S beta. So S alpha is contained in the topological boundary of S beta. If and only if alpha is less or equal to beta. This is where this is how I'm defining the inequality. What inequality means there. Okay. So you say that this is Whitney stratified. If the following conditions hold. So there are two conditions, which is literally called Whitney conditions A. Okay. Condition A and condition B. So condition A says that suppose you have a sequence xn in, so let's just fix alpha less or equal to beta. So fix a pair S alpha S beta such that S alpha is containing the topological boundary of S beta. Okay. Then Whitney condition A says that if you have a sequence xn, okay, inside S beta such that this converges to a point in S alpha, and the tangent spaces to S beta at these points also converge to a plane in the Grassmannian at that point, then the tangent space to the lower dimension of stratum is contained in. So visually it looks something like this. This is S alpha and this is S beta. So you have a sequence of points converging to a point here. The tangent spaces converge to the tangent space here, converge to a plane here, and this should contain the tangent space to the lower dimension. Okay, and then there's also condition B. Okay. Yes. Yeah, I mean, this is already a partition, so they can't intersect. So that actually implies it has to be in the topological boundary. I didn't want to write boundary there because these are manifolds also. So yeah. Okay. So, and then there's Whitney condition B, which says that again fix alpha less or equal to beta. So you have one stratum and another stratum, one containing the boundary of the other. And suppose you have a sequence xn in S beta and also a sequence yn in S alpha, such that both limit to the same point in S alpha. Okay. And also the tangent spaces as before converge to a limit plane. And moreover, the seconds of joining x and yn converge to a line in TZM. Then, so if all this happens, then L is contained in. So what does this look like again? Well, I'm drawing the simplest example. So this is S beta, this is S alpha. Here a bunch of points converging to some point here and a bunch of points converging to some point here. And if you look at the limit tangent planes, that will contain the limit secant. Okay. So what are some examples? Basically, I mean, there are lots of examples. Limit tangent plane contains the limit secant. These I'm saying look at the seconds, they will converge to a line here. Okay. Okay, yeah. Limit of seconds, yeah, right, correct. Yeah, it's not a second of anything. Right? Yeah. Okay. So examples, you can just draw some pictures. So one picture I've already drawn. You just take the closed upper half plane inside R to the 10 or whatever. And you can look at also some cusp cross R. This is also a fine example of Whitney stratified space. Any manifold with boundary, stratified by two stratum, the interior of the manifold and the boundary. And also, I mean, let's just draw this example anyway. You can take, so take pinch torus and glue a disk. I learned this example from Gorski matters. So these are what typically stratified spaces look like. What are some non-examples? Well, you can take a bad spiral, and then the limit tangents converge here, but the limit seconds, I mean, they just converge something orthogonal. Okay. Other interesting non-examples are you take a family of nodal cubics where the node degenerates to a cusp. Okay. Now stratify this family by taking all the node points and their closure. That's one stratum, and the complement. That's another stratum. This is not stratified. This is not Whitney stratified. One can check that. But it becomes Whitney stratified if one also includes the stratum, which is just the cusp point itself. Okay. And this is in general, this is a general phenomenon. Any algebraic variety, you take any algebraic variety in CPN, and you look at this decomposition, the partition given by the non-singular part, the non-singular part of the singular part, the non-singular part of the non-singular part of the singular part, etc., etc. And that is not a stratification, but there is a sub-stratification of that. There is a finer version of that, which will be a Whitney stratification. That's Whitney's theorem. So any algebraic variety can be stratified by quasi-projective variety. Okay. So I want to discuss this intrinsic definition of, there is some extrinsic definition of stratified space, because we started with the subspace of a manifold and then defined what it means to be stratified there. So there is an intrinsic definition of stratified space, which I have already written a priori. So this is what it looks like. So I'll just say what it looks like. I'll just narrate this thing. So take X, a second countable metric space, and you have a partition of X into subspaces, locally closed subspaces as before, where S alpha topological manifold. S alpha intersection S beta closure is non-empty if and only if S alpha is containing the boundary of S beta, if and only if alpha is less or equal to beta. So you have such a thing, X comma sigma. You define a tube system for this partition sigma to be a collection T alpha, pi alpha, rho alpha, where T alpha is a neighborhood of S alpha in X. Think of it like a tubular neighborhood. They think of it as tubular neighborhood of a stratum in a Whitney stratified space, intersect the Whitney stratified space itself. Pi alpha is the projection from the tube to back to the stratum. It's a retract, and rho alpha is the radial distance function. Well, it's called the radial distance function. We should think of it as a radial distance function, but it's just a function from T alpha to 0 infinity, such that the preimage of 0 is all of the stratum itself. And you say, given all of this, you say that this triple X, sigma, and T is abstractly stratified if the following conditions hold. Okay. Each stratum has a smooth structure, first of all, and all the rest of the conditions would say how these smooth structures patch together. So condition 2 is that, okay, so I should give you a notation here. So I have defined what tube of S alpha in X is. I can also define tube of S alpha inside S beta. How is it defined? Just take the tube, intersect with S beta. Okay. So a picture here would be, yeah, let me draw it here. This is S alpha. This is sort of the tube, and this is S beta, some stratum abutting S alpha, and you just intersect the tube with this. This is T alpha beta. This is S beta. And pi alpha beta, rho alpha beta simply defined with the restrictions. Pi alpha beta, rho alpha beta, these are maps from manifolds, right? Because T alpha intersection S beta is a subset of S beta, submanifold of S beta, open subset. These I demand to be smooth. I also demand that pi alpha beta, rho alpha beta from T alpha beta to S alpha cross 0 infinity is submersion. So they define something like a partial cylindrical coordinate for the tube. And finally, these are the most important conditions. You have the pi control condition, which says that for all alpha less than beta less than gamma, pi alpha beta compose pi beta gamma equal to pi alpha gamma, and rho control, which says that rho alpha beta compose pi beta gamma equal to rho alpha gamma. Okay, so what are so beta to alpha. Pi alpha beta means projection from beta to alpha. Yes. Okay. Which one? Sorry, this condition. X and Y and bar means this the secant joining X and Y. Yeah, so you can choose the coordinate chart so that the sequence are defined, and this definition does not depend on the coordinate chart by chain rule. Choose a coordinate chart near a point so that this is defined. No, that's true. That's true. You can check that. That's true. Yes. Chain rule. I mean, it
Why? Yes, it's really a straight down, like,
yes.
with local.
Yeah, locally, of course. I'm taking a point P in the lower dimension stratum, then taking a chart, then intersecting with the stratum, and then defining this. Also, alternatively, you can work in the second variety, right? You can take M cross M and then work there abstractly. Take M cross M, blow it up on the diagonal, and then this is completely intrinsically defined. But that's too much to say. So that's okay. Yeah, if this, yes. So I mean, the point is that if this fails for some local chart, I mean, if this holds for some local chart, it will hold for other local charts. That's what I mean. Okay, so these control conditions, what do they really mean? Okay, I'm just draw a picture. Yes. Yes. Okay. Thanks. So take this very simple example of an abstractly stratified space, which is just R2 stratified by origin, complement of origin in the real line, x-axis, and the complement of the x-axis itself. Then an abstract stratification here looks something like this. You have a tube for this is S alpha, this is S beta, this is S gamma. Right? So you have a tube for S alpha, which looks like let's say S alpha, tube for S alpha inside S gamma. Right? This looks like, or this is T alpha. Right? T alpha looks like this, and T beta looks like this. These will be tubular neighborhoods of the stratum, but these are non-compact, so they will be non-properly embedded tubular neighborhoods. Okay, and what are the projections? The projection from T beta, so this is T beta, to pi beta is the projection. So the pi fibers look like these. Fibers of the projection look like these, and as you get closer and closer to this point, they should bend. I'll explain why. This is basically condition 2 here. And the radial distance function, the radial distance function here are the preimage of the radial distance function. I mean, the level sets are these circles, right? Distance from origin to anything. So that's why I made this lines bend, because then only this condition will be satisfied. If you take a point here, project, measure the radial distance, that's the same thing as measuring the radial distance before projecting. That's what it means. All right. So it's a theorem that Whitney stratified if and only if abstractly stratified. So this is a theorem. And yeah, I will. Yeah. So this direction is by Thom and Mather, and this direction is not so. Okay. So what this means is that any Whitney stratified space, we can abstractly stratify it by genuine tubular neighborhood of the stratum inside the manifold, because it's already embedded where all these conditions hold. And conversely, any abstractly stratified space can be embedded inside a manifold in Euclidean space such that there exist tubular neighborhoods where this condition is satisfied. Okay. So finally, we have we know what stratified spaces are now. Let's just define symplectic stratified space. I don't remember maybe 80s. I don't remember the date. Sorry. Okay, so symplectic stratified space. Okay, what is this thing? Start with a Whitney stratified space. And take a form in the ambient manifold. We will say that, so definition, omega is symplectic on if omega restricted to each stratum is symplectic. Sorry? Yeah, necessarily. Okay. So this is the obvious definition if you want to define, for example, symplectic manifolds using the Green-Pollock definition of manifolds, right? It's already embedded somewhere. So how do you define it? You define it so there's a form there which is not necessarily symplectic, but restriction of the form to each stratum is symplectic. So examples include projective algebraic varieties, singular this time. There is a, by Whitney's theorem, there is a stratification by quasi-projectives, and you restrict the symplectic form, Kähler form there on each quasi-projective stratum. That will give you a symplectic form on each stratum. Okay. And another example is you have G on M omega Hamiltonian, and you take the symplectic reduction. Okay. So this is an example. So it was shown by CMR and Lemma in 91 that this is something they call so they also call it a symplectic stratified space, but it's a Poisson algebra variant of a symplectic stratified space. So you have some Poisson algebra structure on the algebra of smooth functions here, such that inclusion of each stratum gives you a Poisson algebra homomorphism. So that they proved in that setting, this is a example of a symplectic stratified space, and we have been able to improve it to show that this is, I mean, we have been able to use it to show that this is actually a example of a symplectic stratified space in our sense. Okay. Sorry. So CMR and Lemma said that, so they have proved that this is an example of a symplectic stratified space, where their definition of symplectic stratified space is you have a Poisson algebra structure on M double quotient G, the algebra of smooth function from this one, and restriction. So if you look at inclusion of each stratum inside the whole space, that gives you a map from C infinity M double double G to C infinity stratum. This map is a Poisson algebra homomorphism, and each stratum is symplectic. Yeah, so their definition of a, so their algebra of smooth functions here is you no, their definition is not that. So their definition is, so you think of this as mu inverse 0 mod G. Mu inverse 0 you equip with this algebra of smooth functions from coming from the ambient M. C infinity restriction, so all smooth functions restrict to mu inverse 0, and there you take the invariant G invariant functions, GIT there. Yeah. Yes, C infinity mu inverse 0 G. Yeah, it's equivalent. That's what we've proven. Okay. So off to Gromov-Tischler theorem. Yes, exactly. So here's a theorem. Suppose M omega is symplectic manifold and omega is integral, which means that class of omega is contained in the So class of omega a priori is containing H2MR, so it's actually containing H2MZ. Then there exists an embedding from M to CP some huge N such that F star omega scalar is equal to omega. That's the Gromov-Tischler theorem for manifolds. So this the Gromov-Tischler theorem. This is by Gromov and Tischler. Yes. So this is by Gromov and Tischler. Yes, thanks. That's actually extremely important. Compact. So this is like a flexible version of Kodara's embedding theorem. So if you have a scalar manifold, then the Kodara says exactly the same thing. You have a scalar manifold, compact scalar manifold, and this is the integral class. Then there exists a complex analytic embedding in their case, complex analytic embedding from M to CPN such that F star omega scalar is not omega but some multiple. So the natural question is, does it work for symplectic stratified spaces also? Okay. For this, what we need is to say what cohomology means, right? What is cohomology class of a form? Okay, so let me say a few words on that. So Durham cohomology for stratified spaces. Yes, please.
So your notion is strictly much more general than this, right? There's only a class.
No, though, so their definition of a, so I specialize their definition to this one. So their definition is that you have a Wheaton stratified space and you have some subalgebra of the algebra of continuous functions, which has the property that any function there is, if you restrict to each stratum, it's smooth. Some subalgebra. And that has a Poisson structure such that restricted to each stratum, it is a symplectic structure. The Poisson structure is symplectic. That's their definition. It's, yeah, it is pretty general, but no, this is the 91 paper where they proved that this M double quotient G is in fact symplectic. Yeah, there are three papers. I'm not sure if I remember. On X, yes, some subalgebra you have such that if that has a Poisson algebra structure such that if you restrict to each stratum, you get a symplectic structure.
Since that here at least you're using a smooth form to tie in the various strata together. There is no somehow smoothness.
Yeah, the smoothness is this just. Sorry, how do they get a Poisson algebra structure? Yeah, I mean the Poisson algebra, the Poisson structure will give you omega, right? I mean that's their I should say that's their hypothesis. The Poisson algebra restricted to each stratum should be non-degenerate. Which means that it's given by a symplectic form. A priori, a Poisson algebra is like a symplectic foliation, right? And they are saying it's non-degenerate, so there is only one leaf, so it's just one symplectic form. Okay. So what is Durham cohomology for stratified spaces? Well, you can give two definitions. Suppose that X, sigma, and P is an abstractly stratified space, and you have embedding inside a manifold where it becomes Wheaton by an semester. So one thing you can do is you can take so this is what I would call smooth Durham cohomology. Smooth Durham, which is you take all forms on all smooth forms on M, and then you pull back the sheaf on X, and then this is a resolution of Rx. This gives a complex of a complex of fine sheaves, which resolves the constant sheaf on X. So it will compute for you the RAM cohomology. Compute for you the RAM cohomology of X. Well, the singular cohomology of X with coefficient in R. So this is like saying you take a small regular neighborhood of X inside manifold and then do RAM theory there. It's a manifold, so you can do it there. Okay, but this requires some extrinsic choice. You can do it completely intrinsically, which is due to Verona. Okay. And it is given as follows. Suppose you have definition. Suppose you have a collection of forms omega alpha fine I on each stratum. You say that this collection of P forms. You say that omega is controlled if they patch nicely in the following sense. Pi star alpha beta. So alpha less or equal to beta. So beta is the higher dimension, alpha is the lower dimension. Pi star of alpha beta. If you pull back omega alpha from the lower dimension stratum by the tubular projection, you get omega beta. Sorry, omega alpha is defined on S alpha. Yes, so I should say that. Is inside omega p S alpha for each alpha. Okay, then you say they are controlled forms. So controlled forms also form a sheaf. Fine. Sorry. Pi alpha beta is defined on tubular name. I'm saying omega alpha is defined on all of the stratum S alpha. Yeah, and then this holds on some tubular tube of alpha around beta. And then this also forms, so let's just call it controlled, right? So if you just say that this is omega dr and this is omega dot controlled forms. So this also computes the singular cohomology of X with coefficients in R. So that's another different theory of differential forms. Okay, so but these are abstractly isomorphic. So what is an explicit isomorphism between them? So there is one, and it's given as follows. So there is, yeah, it's just all sheaf of all controlled forms. Okay. So one can construct an explicit isomorphism between these two theories, and it's given as follows. So for this, I need a tool. The tool is what I would like to call a compression lemma. So you have X embedded in M. Yeah. So you can stratify the manifold M itself by X and the complement of X in M. Okay. Let's fix the stratification. So stratify M. We just write it like this. And then you can give it a tube structure. I mean, you can abstract stratify it also by taking the tubes here and the tubes here to be the tubular neighborhood of the stratum in X inside M. So you have an abstract stratification on M itself, in which X sits inside as a substratified space. Okay. So there exists. So for any, so let's say epsilon is small. There exists a homotopy from M cross I to M such that 1 pi is smoothed 2 with respect to the smooth structure in M. 2 is phi S is isomorphism of abstract stratified spaces for all S in 0, 1. What this means is simply that the stratification is it's stratum preserving, it's a diffeomorphism stratum preserving, and if you pull back the tube system by phi, you'll get an equivalent tube system, which means that they are same up to shrinking. radially shrinking and so on. Oh, yes. 0, 1. So for up until 1, it's isomorphism. At 0, it's in fact identity. So starts at identity and ends at something. So what is that something? For all alpha less than beta, you also have this. This does nothing on for all s. This does nothing on s beta minus a tube of radius 3 epsilon around alpha. So what this means is you take T alpha, then you intersect it with the subset given by rho alpha less than 3 epsilon. Rho alpha is the radial distance. That's what this notation means. And finally, sorry, okay, yeah. And finally, you have condition 4, which is for all x in x, phi x1 is equal to phi dx1. Hopefully you can see this, where d is the deepest stratum of x intersecting t d epsilon. Okay, what does all of this mean? I'll explain what the map is for this case. Right, there is a stratification of there is a stratified space, and I've embedded in M, and I've given M the abstract stratification. This one. Okay. So what does this map do? It is given as follows. First, M is R2. M is R2, and X is R stratified by origin and the complement of the origin. Okay. What does this map do? Well, first, it is composition of two maps. First, take the map which radially which takes R2 and then radially, so it is constant on everywhere outside these two tubes, and inside in a smaller tube it shrinks everything to the, it compresses everything to the stratum R minus 0. Okay, and in between it's a smooth interpolation, so it's like compressing these things. Okay, of course you can do it smoothly. And then there's another map which compresses everything here, takes a ball here, shrinks this ball to a point and leaves everything identity outside and smoothly interpolates in between. Compose these two maps. Then it has the effect that it does does the operation of pi alpha for all pi alpha beta for all alpha beta simultaneously. Okay, simultaneously compresses neighborhoods of all stratum to the stratum back. Okay. And then the isomorphism is simply given by between the two theories, two Theorem theories, is given by, so one is there's a natural inclusion from controlled forms to the extrinsic Theorem forms, right? Which is just take omega alpha, take a control form which is just a form omega alpha on each stratum, and then look at so suppose pi alpha is the map from a tubular neighborhood of S alpha back to S alpha. Right? These are the tubular projections of each of these strata inside the manifold. You look at pi alpha star, omega alpha. These are forms on tubular neighborhoods of S alpha, and these patch together because that's exactly what being controlled means. These patch together. So there is a chain map like this, and then there's a chain map which goes the other way, which is you take a extrinsic smooth form there, smooth Theorem form there, and you get a controlled Theorem form by applying pi star omega and restricting it to each stratum. Oh, sorry, here pi 1, I mean, sorry, okay, yeah, should be fine. So notation, the compression map will be called pi, which is the end of the homotopy, right? The final map which does this, there's a process which shrinks everything until everything gets shrinked. At the end, what you get is this map pi. I'm calling it capital Pi because it does the job of all the little pi's at once. So take any smooth form which is a priori not controlled, pull back by pi, and that makes it controlled because that it does the job of pi alpha for all alpha, and then restrict to each stratum. That will give a control form. And these two give you a chain homotopy equivalence between the theories. Okay. M, yeah. Which one is the stratum? M minus X, yes. 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 Yeah, I could have extended to full stratum. Yeah, that's true. That's true. That's true. But here I'm just only working with X. That's what I care about, not the full stratum. So, all right. So, yeah. Yes.
You're only using the one. Why are you doing it? And the others at other places, the isotope. For the other values.
Only I'm using one. Yes.
They're only using
Right. So I'll explain why I'm doing it. I'll explain. I'll explain. Sorry. I should use some other board. 5 minutes, right? Yeah, that's okay.
Yeah, you can ask.
Yeah, no, it will be addressed during the discussion. 5 minutes is quite enough. Okay. So finally, we can discuss Gromov-Tischler theorem for stratified spaces. Okay. The whole problem there was, so we can take a symplectically stratified space, X sigma in M, symplectic form, omega, so which means omega is the two form on M, which restricts to symplectic form each X. So
This might actually. You're likely going to say that this is symplectic form that restricts.
yes.
The word is an attached to here.
Oh yeah, sorry. Form omega. So yeah, okay. So form omega on, let me just say form omega on in the smooth diagram sense, right? In a neighborhood of X, such that omega restricted to S is symplectic for all S. Okay. Now so there should be an integrality condition which would tell you that it in fact after if you satisfy that, you can embed X inside some huge CPN where the Kähler form restricts. So you can overcome the fact that omega is not symplectic on all of them. You can replace them, re-embed so that omega is in fact symplectic, and this is the symplectic form which restricts to each stratum. Okay. So for that I need a Chromology class, but omega is just a form here. It's not even closed. Only restricted to each stratum is closed, not even closed. I can take the theorem Chromology, right? Smooth theorem Chromology. But I can pull back by this pi. Say that omega is integral. If pi star omega, this guy is a controlled form, and this is closed. Why? Because d pi star omega, yeah. So pi star omega is like, so it is like pi star s omega, right? Where s pi s is the projection from tube back to the stratum S, and omega restricted to S is closed. So d pi star omega equal to pi s star d omega, and d omega on stratum is closed. So therefore that's 0. So this is closed as a control form, and I can take its cohomology. Yes. So I say that this belongs to this H2XC through all the isomorphisms. Okay. And then the claim is, then the theorem is that, okay, if omega is integral, there exists an embedding, symplectic embedding, f from X to CPN for some n large, where symplectic here means that F star of omega scalar is omega but restricted to each stratum. I'm allowed freedom outside the stratum. So that's the theorem. So how much time do I have? If I have some time, then I can say it. 3 minutes. Yeah, that's fine. Yeah, perfect. Okay. Yeah. This is only true when you restrict to S. It's not true germinally. This F star omega scalar is a smooth de Rham form. Omega is also a smooth de Rham form. There is no reason that away from. Exactly. Okay. Fine. So let's discuss the proof strategy a little bit. Sorry? Example for X, which is what? Oh, so the symplectic stratified space, which is for such that is integral. I mean, the examples I sort of know are, I mean, either it's, so I basically the two examples I know are complex projective varieties, where it is tautological, it's already embedded in CPN, and the symplectic reduction, which we prove that these are examples of stratified spaces, symplectic stratified spaces. So these are the only two examples that I broadly know about. And every other example, this theorem says that it embeds in CPN, sits inside CPN somehow. No, I don't think so. I don't think that's true. I don't think that's true. Is that true? I have to think about it. Yeah, it should be true because omega there is the symplectic form on M double quotient G is actually induced from the symplectic form on M. Look at M, then restrict the symplectic form on mu inverse 0, and then you quotient to G. So and omega, if omega on M is integral, then that should be true. Okay, so proof strategy. Yeah. Okay. Proof strategy is as follows. First, so this theorem is sort of like an H principle, okay? Because in general, yeah. So how do I explain this? 1 second. So I can say it as follows. Okay. So first we solve the formal problem. The formal problem is find a map at all. Find a map at all from X to CPN, not a symplectic embedding, nothing, such that F star of omega scalar, the cohomology class is equal to the cohomology class of pi star omega. I know this is in H2XZ. Find a map at all. Well, how do you do this? This is simple. Take a neighborhood of X in M, okay, and then you know that H2UZ is isomorphic to U CP infinity, because CP infinity is a KZ2, H2 is represented by KZ2. U is a finite dimensional manifold. U is a neighborhood of X. So you can reduce this infinity down to some big N. So you have a map U to CPN, because this isomorphism is given by, so there's an abstract isomorphism, but some argument with Unida will tell you that the isomorphism given by, take the Kähler form here, pull back by this map. Okay. And so therefore you have a map from U to CPN such that pullback of the Kähler form is the homology class is exactly of the same as pi star omega. So I found a map. which satisfy this condition just at the level of cohomology. So now so we want to go from formal to actual, right? So what this formal thing tells you is that f star omega scalar is equal to pi star omega plus d alpha, right? You want to get rid of this d alpha. So let me write it even better. So pi star omega, since pi is homotopy to identity, you can write pi star omega as omega plus d alpha prime plus beta. Okay, why is so such that beta restricted to each stratum of X vanishes? So why is this true? It's because pi star omega minus omega, this is like phi 1 star omega minus phi 0 star omega, phi t being the homotopy. So which is the same as integral d dt of phi t star omega from 0 to 1, which is the same as Lie derivative del t phi star omega. This is the full homotopy from m cross I to m. And then you use the Cartan's magic formula, which will tell you that this is I del t d phi star omega plus d I del t phi star omega. D comes out, that's this alpha prime. So alpha prime is equal to integral 0 to 1 I del t phi star omega, and beta is equal to integral 0 to 1 I del t d phi star omega. Okay, and you observe that beta is actually 0 on each stratum. Why is this true? Well, they feed it, beta is what? It's a 2 form, right? So feed it v1, v2. That's the same thing as feeding this thing v1, v2 and integrating, which is the same thing as taking, which is the same thing as yeah, phi star and d commute. So make d go inside. Phi star d omega. I del t phi star d omega. Let me write it like this. Phi star d omega. And then this is the same thing as phi star d omega del t v1 v2. Okay. D omega is 0 on each stratum, and phi preserve the sense stratum to stratum. So therefore d omega equal to 0, which means that beta is 0 on each stratum. So exactly. So omega equal to, let me write this is alpha double prime. This is alpha prime, alpha double prime. Let me just write alpha as sum of these two plus beta, where beta restricted to X equal to 0. This is a shorthand for saying beta restricted to each stratum is 0. Okay, so that we have this much. Now we want to just get rid of d alpha. Then we'll be done, because f star omega scalar equal to omega on X. That's what you want, right? So how do you get rid of d alpha? This is, let me say, should keep it here. Let me say just 3 sentences on this. The idea is choose an open cover. So yes, choose an open cover, and such that with respect to that open cover, if you use partition of unity, you're going to write alpha as f1 dg1 plus fk dgk. This is an open cover of X. X is compact, so I can choose a finite open cover. Maybe I missed compactness there in the hypothesis, but X is always compact. Okay, so f alpha can be written like this, which means that f star omega scalar, let me write omega scalar as omega n. No, I need this finitely many terms here. For that, I need a finite collection of open covers, right? X should be compact. So f star omega n being the scalar form of CPN, right? F star omega n is equal to, oh, I should have said that this map in general is not an embedding, but if you take high enough n, it will be an embedding, homotopy to an embedding, so no problem. F star omega n is equal to omega plus summation dfi wedge dgi I equal to 1 to n plus beta restricted to x is 0. This basically doesn't matter. Okay, so what do? You think of, so the first step is stabilize, increase dimension of the target. Think of this map X to CPN as, this is CPN, This is CPN plus 1 and this is CPN. X is mapping inside CPN. Okay. The second step will be to modify this map F inside CPN plus 1 so that one of the terms go away here. Second step is corrugate. I'll explain why it's called corrugation. So you modify the embedding locally. So this is say that the open cover is U1, U2, U3, etc. Modify on U1 somehow so that this first term goes away. If you pull back by the new embedding F, this will go away. So how do you do that? Just need to find a map from H1 from U1 to C, C being the fiber of the normal neighborhood of CPN and CPN plus 1, O1. Find a map H1 from U1 to C such that H1 star of dz bar is equal to df1 which dg1. And then you define the new F to be just the old F, comma, minus H1. Well, you multiply with the bump function, multiply H1 with the bump function, so it's defined everywhere on M, supported on support of H1 is contained in U1. This is the new embedding. And then if you pull back by this, it will be F star omega minus H1 star omega. H1 star omega is exactly this much. Because H1 maps completely to the fiber, you pull back the volume from the fiber, this term will go away. And then repeatedly induct. So all the terms will go away. So you have to increase dimension, CPN plus 1, CPN plus 2, etc., etc. Okay, so how do you find such a function? And if I draw your picture, then you understand that this is exactly like some kind of corrugation. First, you know F1 comma G1, we are both supported on U1. F1 comma G1 gives you a map from U1 to C, R2. If you pull back dz bar by this map, you'll get df1 with dg1. But this maps to some huge disk, right? So large disk. What I want to do is some kind of small perturbation so that it doesn't interfere with anything else. So I want a map to d epsilon 1 such that dz bar, if you pull it back, you'll also get df1 with dg1. So what I would do is I would compose with a map from dr1 to d epsilon 1. Epsilon is very small, or rather unit. Let's just say sorry, this is 0. Unit disk, such that so I need a map like this from a huge disk to a small disk, such that it's volume preserving. F star dz bar equal to dz bar. And what is such a map? Well, visually, you just take a huge ball and then you spaghettify it, sort of stretch in x direction, shrink in y direction, and then you roll it around and put it inside a disk. And that's your map, volume preserving map. That's why locally the graph will also change like this, right? Since you're rolling it around, if you look at the graph, it will change like spinning it around many times. And this is sort of the idea behind Nash's embedding theorem for Riemann manifolds. Yeah, so this is typically H principal proofs are always like this. You have some formal solution and then you corrugate it so it becomes actual solution. And the idea goes back to Nash, which is exactly this Gromov-Tischler theorem, but for Riemannian geometry, which is much harder. Any Riemann manifold embeds isometrically in some Euclidean space. And basically, it's just the same corrugation trick on steroids. Yes.
The manifold is
Yeah.
non-stratified, non-compact case.
Yeah.
Is it true when the CP is or is it true with the finite CP?
Yeah, I'm not entirely sure actually. Yeah, because the same proof definitely doesn't work. You need a finite open cover. Okay, maybe okay, and then it's some kind of technical. Okay, yeah. Right. Okay. Whitney for non-proper. Yeah. Non-compact. Yeah. It doesn't interfere with the local modification shouldn't interfere with the previous modification. So therefore, that's why you can take a sort of limit. Yeah. Okay. I haven't checked that. But yeah. 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 Okay. Yeah. The reason for taking it more and more dimensions is just so that it doesn't interfere with local modifications. Don't interfere with anything else. Yeah, but you can do it if you have a large ball. Something far away shouldn't interfere with what happened here. Yeah. I think the minimal dimension here is also 2n plus 1. Not sure in the stratified scale, but the manifold case is 2n plus 1. Just the Whitney dimension. Yeah, so here you're getting some huge number, right? We pick some huge. We're not being explicit about the dimension. We pick some huge number in the first case, and then you n plus k there. But for a manifold, if you have symplectic manifold dimension n, then it symplectically embeds in R C 2n plus CP 2n plus 1. Yeah, just like the Whitney. This is a one-step stabilization, CPn to CPn plus 1. And then after then CPn plus 1 to CPn plus 2. Because otherwise it might interfere with what I'm doing here, right? The open charts intersect, right? These charts intersect. So FIs get changed. So that it doesn't interfere at all. But of course you don't need that, just being safe. Yeah. So you can see, imagine how you can just do away with for small enough dimensions. How many of these intersect? Yeah, which is exactly topological dimension. Yeah. Right.
So back to the when you're starting with the symplectic reduction.
Yeah.
Using a moment map, does your object symplectic reduction depend on if it's symplectic reduction?
Right. So the moment map is unique if you take some G to be so moment map, two moment maps differ by a element in G star which is in G comma G, which vanishes in G comma G. So if you have a Lie algebra such that it's H1 is 0, then you're fine. I mean, if the Lie group has, G by GG is equal to 0, then the moment map is uniquely defined.
You always have somehow stratified components, or let's say strata in the dimensional distinct, which are of the right expected dimension.
Of dimension dm minus 2 dim G.
Yeah.
It should be true. If G is acting effectively, yeah, should be true, right? It should be true. Yeah, definitely. Yeah. Okay. Okay. Yeah. Sorry, this thing at the end, right? Yes. Here, no, it's just same dimension. This is in C2. Everything here is in C. Sorry, everything here is in C. So dimension raising is happening from CPn to CPn plus 1. What I'm doing is I'm thinking of the map X as sitting inside the graph of Zn plus 1 equal to 0, right? And then making a new graph over that. So how am I doing it? I'm just taking taking this f and then modifying it by putting in Zn plus 1 coordinates some function h from U to disk. Disk in C to disk in C. Yeah, from huge disk in C to a small disk in C. There is a volume preserving map. Just spaghettify it and then roll it around. Okay. Yeah. So I mean, you can write it explicitly, right? So you have some. Okay, so you have some large ball. Okay, this is a large ball, this is a small ball. Okay, and then you apply lambda 1 over lambda here, so it becomes a very long ellipse, and then roll it around. It goes inside this one.